Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. I'm here today with another example of Kirchhoff's rules for circuit analysis. The problem I've chosen to work for you today is one I consider a medium difficulty example because we will end up generating three equations in three unknowns using our junction rule and our loop rule for two different loops within the circuit. So this circuit most simply consists of a top loop and a bottom loop with a shared middle wire. I'm going to start with some reference points to help you more easily identify where I'm working in the problem. So I'll put A in that top left corner, B in the top right, C on the right side of the middle branch, D in the bottom right corner, E in the bottom left corner, and F on the left side of that middle branch. So with my guess that we're going to have a top loop whose current flows clockwise like so, I'm going to say there's a current I1 flowing from B to C, which of course will also be F to A to B, and then C to F is going to have the combined current of the bottom loop too. And I'm going to guess that there is a counterclockwise current in the bottom loop, so that's going to put a current I2 going F to E, E to D. I'll label it over here, I2 going from D to C, and then we'll have a combined current, I3, moving from C to F. So I can set up my first junction rule for the junction at point C, which is that I1 plus I2 equals I3. So let's take now our top loop, ABCF, and set up our loop rule, which of course tells us that the sum of all the potential rises in a loop is equal to the sum of all the potential drops. So following my loop ABCF, I can see I've got one battery, so one potential rise, two resistors, so two potential drops, and I'll remember that I can find the potential drop across a resistor with Ohm's law. Voltage equals current times resistance, V equals IR. So we'll start with our 9-volt potential rise, and then I'm going to have I1 flowing through my 15 ohm resistor, and I'm going to have I3 flowing through my 20 ohm resistor. I'll go ahead and set up my other loop really quickly. So that's going to be FEDC, or I could even do EDCF to keep the lettering a little bit consistent with my first loop. So again, as I follow this one around, I can see I have one potential rise from the 12-volt battery, two potential drops from the 30 ohm and the 20 ohm resistors. So my loop rule for this one is going to be 12 equals 30 times I2 plus 20 times I3. So what makes this problem a little bit tricky is that I have three equations in three unknowns, which becomes a little algebra intensive. So I am going to show you two ways to solve this system of three equations. The first way is the long way and is all algebra. The second way is a shorter way and involves using the coefficients and the constant set up in a pair of matrices. So if you haven't learned matrices, you can just skip over that part of the solution. And if you know matrices, I strongly recommend that you solve it that way because it will save you so much time. So on to the algebra. So to solve this pair of this set of three equations, the blue equation for the junction rule, the green equation for one of my loop rules and the purple equation for my other loop rule, I'm going to be able to substitute I1 plus I2 in for I3. So we will do that now. I'm going to go ahead and rearrange and put the 15 in front of the I1 just for consistency. So when I distribute the 20 to the I1 and the I2 that are in the parentheses, I get 20 I1 plus 20 I2. So 9 equals a total of 35 I1 plus 20 I2. So now I've eliminated one of my variables that I didn't know with that substitution of I1 plus I2 for I3, and now I have an equation that's just in terms of I1 and I2. So I'm going to do the same thing in my purple equation and end up with another equation that's just in terms of I1 and I2. So again, I1 plus I2 goes in place of the I3. Distribute that 20. So I get 20 I1 plus 20 I2. And I have 20 I1 plus 50 I2. So now with substitutions, I've been able to take this system of 3 equations in 3 unknowns and make it a system of 2 equations in 2 unknowns. And those are the 2 I'm going to be able to solve even further. I will put asterisks by the 2 equations that we're going to need for this next step. All right, so let me put my next step of work down here. So one of the ways that you may remember how to solve a pair of linear equations is to multiply one or both of them by a constant value so that you can add the 2 equations and eliminate one of the variables. So in this case, I notice that for those coefficients of I2, 20 goes into 50 2.5 times. So if I multiply my top equation through by negative 2.5, I will end up with negative 50 I2 as that term, and then when I add the 2 equations, I've now effectively eliminated I2. So that's what I'm going to do. And let me check my work over here. So negative 22.5 is going to be equal to negative 87.5 I1 minus 50 I2. And then my second equation there remains unchanged. And when I combine the 2, I get negative 10.5 is my constant term, equals negative 67.5 I1, and then the 50 I2 in the bottom equation and the negative 50 I2 in the top equation have added up to 0 I2. So now I can finish solving here. That I1 will be negative 10.5 divided by negative 67.5, and I will get a value of 0.67 0.15, where the 5 is a repeating decimal, amperes. Let me put that inside a little box to help us keep track of it. So now I can take any one of my equations that involved I1 and I2 and make a substitution for I1. And I'm going to go ahead and make that substitution into my 12 equals 20 I1 plus 50 I2. We'll go ahead and get another color in there to help show that. So substitute that 0.15 for I1 plus 50 I2, and I will get 12 equals 3.7. Actually, give me just a moment. I can't read my own writing. 3.1, sorry. 3.1 repeating decimal plus 50 I2. So I will get 8.8 when I continue with my algebra here equals 50 I2. And I'll get a value for I2 equal to 0.17 repeating decimal amperes. So again, let's mark that one in red because that's also important. And now, last but not least, we can solve for I3, which is the sum of I1 plus I2. Got a little bit of space right here in the middle. And I get a value for I3 of 0.3 repeating decimal amperes. In fact, I actually want to lay that out just a little bit differently. So these more complicated Kirchhoff's rules circuits problems can be complicated just because they're time intensive. There's a lot of math to go into them. So if you're like me and you don't love doing a lot of algebra, let me show you the short way to do this. If you haven't learned about matrices in your math class yet, then you can just ignore this and know that your problem is done. So to solve a system of equations, we can set up, and I'll reorganize them in just a moment, we can set up two matrices where one of them is the coefficients of our I terms in this problem, and then the other matrix is the constant terms. And then if we take the inverse of the coefficients matrix and multiply it by the constants matrix, we get our answer in the form of a matrix. Why that works, that's like linear algebra, differential equations kind of stuff. You don't need to know why it works, just know that it does. So I am going to take, to start, my loop rule ABCF, and I'm going to write it as 15I1 plus 0I2, because here's the important thing. When you're going to set up the matrix, every current has to show up in every one of your equations in order to have an entry in the matrix. There's no I2 in that equation, so we can say it's 0I2 plus 20I3 equals 9. And then we'll take my purple equation and do the same thing. It had no I1 and 30I2 plus 20I3, and it equals 12. And then our last equation is going to be from my junction rule. And I am going to have to subtract I3 from both sides in order to have all of my currents on one side of the equation. And that was just going to be I1 plus I2 minus I3 equals 0. So when I go to enter these coefficients into my matrices, it's very important that the top left entry in the matrix cannot be 0. So I could not use my loop EDCF equation as the first equation that I put in. I could use the junction rule equation, or I could use my loop ABCF equation, because that one doesn't have 0 for current I1. So I'm going to call my coefficient matrix, matrix A. Its entries will be 15, 0, 20. So if you know how to do matrices with your graphing calculator, this becomes easy peasy lemon squeezy, absolutely the simplest thing ever. And then my matrix B is going to be my constants, the 9, the 12, and the 0. And now I can enter, let's pick another color for fun. How about this one? And then when I do the inverse of matrix A multiplied by matrix B, I'm going to get a 3x1 matrix, and its values are going to correspond to I1, I2, and I3. And not surprisingly, you get exactly the same thing as you get working out all of that annoying algebra. So I love the matrix way of solving this problem because it's so much less work, so many fewer opportunities to make mistakes. All you have to do is get it set up right and get it put in the calculator right, and the calculator does the hard work. Whereas I know I still occasionally make sign errors and silly things like that. So you can do whichever one works for you, but my personal favorite is the matrix. Thank you for joining me today. I hope you found today's solution helpful. If you would like some more one-on-one assistance and to explore the possibility of working together in a more long-term kind of tutoring relationship, you can contact me at brandyheflinphysics@gmail.com to sign up for your complimentary 60-minute family discovery session. I'm also currently taking requests for problems to solve at physicsproblemrequests@gmail.com. When you send your problem to me there, you also get the chance to have your problem solved live on my Facebook feed. You can find me at my website, brandyheflin.com, and you can find me on Facebook at Physics Tutor Brandy. I love physics, and I love helping you. Until next time.